Well, hey, hello, and good morning, and welcome. Today I want to give you a presentation about our next project, which is the LED cube project. This is the third project for this class, and you'll get some more experience in this project with FPGA programming, but also get to use the cool LED cube that we really designed for you. So, as an overview for this project, the kind of one new idea that we're going to try to learn about is persistence of vision. It's the idea that if images are, or the LEDs are flickering fast enough, basically you're not even able to see that they're flickering. You see kind of a static image, and that the idea of persistence of vision will be used in the LED cube to create display different patterns or create different static or dynamic images. And I'll also talk about the LED cube hardware and how to control the LEDs and how to interface it with the FPGA board. And then I'll give a very brief introduction about state machines and how to write them in system Verilog so you can write your code. But as usual, just a reminder about our lab safety and the lab rules in general. Make sure that try to keep the lab, like on this picture, everything nicely organized, and kind of when you leave, make sure to push in the chairs and try to organize all the equipment, so it really helps everybody. But getting to the project, so some of the goals for the project: first, to learn about the persistence of vision. Then I'll learn how the LED cube hardware works, and then get some more experience with system Verilog. And then finally, the most exciting part probably is design and write code for LED cube, for the LED cube, or rather for the FPGA to control the LED cube to display some interesting patterns. So this is the LED cube. As you can see, there's the cube itself with a nice blue PCB that was designed last year. There's a 40-pin or 40-wire ribbon cable that goes between the LED cube and the FPGA board. You can see there's a 5-volt power supply to the LED cube, and then there's the USB cable for controlling the FPGA board and also supplying the power to the FPGA. So basically, and the FPGA chip is kind of hidden in this picture under the ribbon cable. So so in this project, you get to put these two pieces together and then write code for the FPGA to control the cube. But just to make this things a bit interesting, first I want to talk about persistence of vision, which is basically a theory that the eye retains the image of any object presented for it for a very brief period of time. So basically, let's say if you flicker two LEDs on and off very quickly, then they'll appear as if they're statically on. And to give you an example from the LED cube, here we have a video that shows you LEDs lighting up on the cube very slowly. You can see that as each row kind of lights up, it kind of slowly moves up and down, but you can clearly see that the LEDs are turning on. And then if we go to the next video, we sped up the operation of the LED cube a little bit, so now the LEDs are turning on faster and faster, and you can still obviously see that they're flickering on and off, but it's kind of becoming more smooth. And then finally, as a last image, this is also the LED cube, and all the LEDs are flickering again, except now they're flickering so fast that you don't actually see them turning on and off. So it looks as if the whole plane is constantly on. So so you can see kind of very slow, medium, and then very fast flickering. And in the last case, you can almost see it as a plane. So and that is because of the persistence of vision. If you turn on and off LEDs kind of faster than your eye can react, then it will seem to you that all the LEDs are on at the same time, and you can create this illusion of like, let's say, of this horizontal plane. And one reason we'll be using the persistence of vision is that we can't actually control all the individual LEDs in the cube at the same time. I'll explain it shortly. It's basically to save on number of wires that you have to send between the FPGA and the LED cube. But still, because of the persistence of vision, you can create an illusion that you can control these LEDs such that it seems that they're all on, even though actually at each instant they're not actually all turned on at the same time. So yeah, so this is a very brief introduction to persistence of vision, but we'll use it in the design of the LED cube. And now I want to talk to you more about the LED cube hardware, and you'll soon see how the persistence of vision comes into this picture. So again, this is the same picture I showed at the beginning. Again, you have the LED cube, you have a power cable, you have the ribbon cable, the signals, and then you have the USB for programming the FPGA board. Yeah, and then this is a zoom-in structure of the LED cube, so you can see that they have the 40-pin connector on the bottom for the ribbon cable power supply. The black semi-round elements are the transistors that are used to control the LEDs. You also see these resistors. You already saw resistors in the breadboarding project, so that should look familiar. And this is the LED cube structure itself. You have these big blue LEDs, and these metal wires are actually the structure of the cube, but also they're used to supply power. So you can see that each LED has two legs, and then they're connected to different wires, so that basically they can supply ground and VDD to each LED. So make sure not to touch the wires together, because otherwise you may short circuit the whole design when the power is on. But if you're not touching it, then basically we're using the structure itself to build the cube, but also to provide the power. And now about the LEDs, they're basically controlled. There are two sets of control signals that you can use. So it's a 3x3x3 LED cube. So there are 27 LEDs that you could control. However, that would require you 27 signals, which does not. And as the cube gets bigger, you would need the dimension cubed signals to control all the LEDs. So instead, there's a neat trick that is used for this cube, in that there are three signals that control each vertical plane. So there are three vertical planes that can be separately turned on and off, and then there are 9 signals that control each horizontal row. So each plane has 9 LEDs. So effectively, you can control all the 9 LEDs. All the 9 rows of LEDs independently, and you can control the 3 vertical planes independently, but you cannot control all 27 at the same time. And so the benefits of this design is that there are fewer control signals, and it's easier to build the LED cube structure. So if you had separate control signals for each of the LEDs, then you'd have to have dedicated wires, ground and VDD going to each LED. And instead, we can spread these wires out, and there's less wires going around. Now, the drawback is that you can't individually control all the 27 LEDs at once, and to displaying certain patterns on the cube, you need to use persistence of vision. So here comes some examples. So for example, if you want to display an image like this with just 2 bottom LEDs, then you can turn on the row 1. So row 1 is the row in which these LEDs are. And you can turn on the vertical planes 1 and 2. So by turning on the vertical planes 1 and 2, only LEDs in those planes can be on. And then, in addition, all the LEDs in row 1 are on. So, for example, you see that the third LED is off. It's because the third plane is off. So, if you turn on both vertical planes 1 and 2, then you couldn't have a different pattern than what you're seeing. And here, for example, to show all the 9 LEDs in one of the plane, you turn the vertical plane 1 on, and you turn all the 9 rows. So all the 9 rows are turned on, but because only plane 1 is also turned on, the other 2 planes are staying dark. So for these patterns, you don't need persistence of vision. Now for the third pattern you do. So again, this is the diagonal pattern, and we have the video to, again, you can see that, sort of see the LEDs flickering, but pretty much seems like a horizontal plane. And to achieve this effect, first you have to turn on all the bottom rows, so the 3 LEDs on the bottom are turned on, and you turn on the vertical plane. So if you turned on all the vertical planes, then you'd see the bottom turn on, but in this case we turn on just the bottom rows and the first vertical plane, so you get this kind of like a column of LEDs. And then in the very next instant of time, you turn the vertical plane 1 off, you turn the bottom rows off, and you turn the middle rows on, and the vertical plane 2, which gives you this this middle column. And then the third step, you turn on the vertical plane 3 and all the top rows, which gives you the last column. And then if you repeat these 3 steps very quickly, one by one, again, you can see the video here that it basically you can't even see that it's flickering on and off. It just stays a constant plane. But in reality, what the cube does, it constantly does these three operations. So yeah, so for this, so for example, for such a so for some patterns, as I showed here, you don't need the persistence of vision, but to display patterns like this, you need the persistence of vision. So yep, and yeah, so that's how the LED cube works with the wires, and the individual wires are connected to the FPGA via the 40-pin ribbon cable, and the ribbon cable has what's called keyed connectors. So basically, the connector is designed such that you can only put it in one way. You can't put it in backwards. There's a little notch on the side of the connector. So a keyed connector basically means that there's a key, or there's a special side to the connector to make sure that that it only goes in one way. So there's no way to put it in backwards. All right. So hopefully that gave you an overview of the LED cube structure, and I can give you some brief introduction to system Verilog and state machines, which you'll need to implement for to controlling the LED cube for this project. So again, before we get to that, just a brief overview of the FPGA. So again, this is your FPGA board. That there's the FPGA chip itself. There's the USB for programming and power. We have the LEDs, 7-segment display, input switches, and a new feature of the board that we'll use is this GPIO connector. GPIO basically means general purpose input and output. So in this case, these are 2 GPIO connectors, and they each have 40 pins. You can't actually use all of 40 pins. You have to look at the manual for details, but most of these pins can be used to access basically external to send or receive external signals, and the pins themselves are connected to the FPGA. So again, this is the zoomed in picture of the FPGA, and what you should know is that the physical pins that are in the GPIO connector are actually physically connected to the FPGA chip. So we already talked about it. So inside the FPGA chip, elements and little routing elements that basically let you implement they realize the logic that you write in system Verilog. Now, something that we haven't talked about yet is basically if you look in the if you were to kind of look on the underside of this FPGA chip package, you'd see something like this image. So this gray dark structure, block structure is the package, and inside is the FPGA chip, but the FPGA chip has actual pins that are connected to the outside world. So you need to supply power, you need to program the FPGA chip, or you need to interface with the external world. So the FPGA chip inside the package connects to these pins. So if you took off the FPGA package from the board, either you would see there's a ball grade array, or these are just regular pins that are sticking out, and these have electrical connections to inside the chip. And then if you look on the blue PCB board, there are little tracks of wires that some of them go from the FPGA chip to the GPIO connector. So when there's a connection between some external wire and a pin on the GPIO, there's also an internal electrical connection on the PCB board between that pin and one of those pins on the FPGA chip. So that's how the FPGA chip interacts with the with the outside world. And so there are a couple of different pins involved here. So just to kind of summarize, so there are the FPGA chip pins. So there are pins on the actual FPGA chip itself. If you open the pin planner, if you remember in Quartus, there's a pin planner. It gives you kind of an image of all the pins, and you can assign internal signals to those pins. So that image pretty much corresponds to an actual underside of the FPGA chip with kind of all the pins, and it shows you which pins are what. So there are the FPGA pins, the GPIO pins. So some of the FPGA pins connect to the pins on the GPIO connector. So you have to look in the manual for the FPGA board to figure out which GPIO pin connects to which FPGA chip pins. And finally, there are the pins on the LED cube. So the 40-pin connector on the LED cube also has some pins. So there are different sets of pins that you need to be they're all called pin, but you need to worry about the FPGA chip pins, GPIO pins, and the pins on the LED cube. So and then by sending the appropriate signals through the FPGA chip, the chip pins to the GPIO pins to the LED cube, you can actually turn on and off either the vertical planes or the 9 rows of LEDs, and the lab manual will tell you which pins are controlling what. So so that's the overview of kind of how to interface the FPGA chip to the LED cube. And as a last part, I just wanted to give you some brief introduction to the state machines and system Verilog implementation of state machines. So what is a state machine? So a state machine is or a finite state machine is basically a mathematical model of computation, and it's an abstract machine. It's an abstract model that basically represents a finite number of states that your system can be in, and then your finite state machine can only transition from one state to the other. So here we have the state machine. So here we have the state machine for the very simplified state machine for the LED cube. And let me run the animation again. So you have some idle state or start state. Then you have, say, the first state that let's say corresponds to the vertical plane 1. Then you have the second state, that's vertical plane 2, and the third state, that's the vertical plane 3. So the way you can think about it is that basically this the system or the code that you write for the hardware will implement a state machine like this, and when you're in the vertical plane 1 state, then the first set of LEDs turns on. Then you move on to the vertical plane 2 state, where the second set of LEDs turns on, and then you move to the vertical plane 3 state when the third set of LEDs moves on. So the state machine basically is a set of states, and you deterministically move from one state to the other to achieve the operation of your system. And in our case, for now, there will be no real inputs. Basically, once you enter the first state, then when the clock edge comes, you go to the next state, and then you go to the next state, and you go back, and you kind of, by circling back and forth, you'll be able to achieve this effect that, the state machine circles through the 3 states. In each state, different set of LEDs is turned on. And then if you increase the clock speed, so if you increase the frequency with which you visit each of the states, then the animation will go faster, and eventually you're not going to see any blinking of the LEDs. It will seem like the horizontal plane. As a very brief introduction to how to do the state machine in system Verilog, there are basically 2 or 3 parts that we need to learn about. So first, you need to define the states of your state machine. So typically you can use something like a type def. So you define a new type. The name of this type is state t. So like an integer or rather a wire or a register is the type. You can define a new type, which is state t. And then this type uses 2 bits, so 1 to 0, so it uses 2 bits. And these 2 bits will represent 4 literals or strings, or in this case 4 states, which is idle, light 1, light 2, and light 3. So by having this type def, you define 4 states for your state machine, and then the next statement, state underscore t state. That means that now that you've defined this state t type, you define a new variable state, which can take on one of the four values: idle, light 1, light 2, or light 3. So the second part is you need to define a process that basically controls how you transition between the states. So here you use an always ff process that will create flip-flops where you store some information, and in this case the state is the information that you're storing. So and then always ff is sensitive to positive edge of the clock or the negative edge of the reset. So there are 2 inputs to the state machine. There's a clock, so pretty much every state machine will have a clock. So in each clock edge, your state machine will do something interesting. And we have a reset signal. So actually, if you look in the manual, the reset is connected to a button. So when there's a positive edge of the clock, or if there's a negative edge of the reset signal, something interesting will happen. And inside this always statement, then if reset n is 0, so if the reset signal goes to 0, then you set your state to be idle. So the state of the state machine is idle. Otherwise, if it's not reset, then the clock edge must have happened. So then otherwise there are a couple of cases. So if your state is currently idle, then you wait. Then you see if there's some go. Go is going to be a button that we will show you how to implement in the code. So if the button, again, the value becomes 0, then you jump to state light 1. Otherwise, nothing happens, so state stays idle. And then if you do go to light 1, then you go to light 2, and light 2 you go to light 3, and then light 3 you go to light 1. So you can see in this very simplified state machine, once this go signal becomes 0, you enter the light 1 state, and then every clock cycle you'll go between these 3 states back and forth, and basically forever you will circle. So your state machine, as this picture shows, once the start or idle, you kind of get stuck in these 3 states and you circle forever, and then so your machine is running as long as the FPGA is powered. And then to actually do something, so here you just define the state transition. So actually this one process combines the state and then the next state computation, and you also need some output to do something interesting. So this is a combinatorial, so always com is a combinatorial block of combinatorial logic, and basically again you have a case statement. So if you're in the idle state, then let's say the row 1 bottom is 0. So let's say this variable represents the bottom row, and the row is turned off. And then when you have light 1 state, then the bottom row 1 is on, and then in light 2 it's off, and in light 3 it's off again. So if you remember the animation, in the first step you turn on the bottom rows. So here we're just showing the row 1 on the bottom. So in the first step, in light 1, the row is on, and then in the next 2 states it's off because you're turning the middle and the top rows. And then again, when the state control gets back to light 1, then again the row 1 gets turned on, and then kind of go on and on and on and on. So so in the lab manual we'll give you a fuller example of the state machine, including how to define the states, how to do the state transitions, and how to generate the output. So and as final review, just again, you write your specification in system Verilog. In this case, you'll be writing these state machines. Then you synthesize the design to the FPGA and actually program the FPGA. And then once the FPGA is connected and programmed, we'll also tell you how to connect which pins connect to the GPIO pins and the LED cube. So once your state machine is running and assigning values to these row and vertical plane control signals, you'll be able to turn on the LEDs on the LED cube. So just to summarize, yeah, hopefully you learned a little bit about persistence of vision. I tried to explain how the LED cube structure works, how to control all the LEDs, although you don't have 27 signals for controlling them. Some very brief introduction to state machines in System Verilog, and then as a last part, just showed you some examples for the LED cube, and that's effectively what you have to do for this project, is to understand persistence of vision, learn about the LEDs, write the code, and then demonstrate a working cube. So, okay, the most important part, the evaluation. So again, we're doing these 2 levels. So for the 90% level of the project, you have to follow the lab manual, implement the FPGA code for controlling the LED cube, and you have to create an animation of a horizontal plane kind of spinning. We give you just the code for the animation that I showed you, where one plane is on, and you have to expand it by adding more states to make the plane actually spin, and then answer some brief questions and write the lab report. And then for the 100% level, again, open-ended. You can pick anything you wish. You can do some additional animation. And yeah, this is a 2-week project this time, so we're back to 2-week projects. Please read chapter 4 of the book. You can utilize the open lab hours to work on the code and testing. So you might have to spend more time on this project. And the Quietus software should be still available for free for Windows or Linux. Actually, there's a typo here, so unfortunately Mac is not supported. So Windows or Linux, but you can actually write the code in any text editor and bring it to lab. So yeah, don't procrastinate and start early. And as final step, just the usual acknowledgments. Kevin Ryan again for all the help with the LED cube PCB design last year and kind of assembly and testing. Beth Seeley, who's one of our assistants in lab, for helping with the assembling of the cube and some of the wires and parts. And Wenjie and Wen, again, they also helped a lot with soldering and assembling everything. So thanks to them for putting this together for you. Last but not least, some of the background text for the persistence of vision and the finite state machine was from Wikipedia, so you can read more details there as well, or in the book about the state machine. So that's it for today. Thank you so much. Hope you enjoyed the LED Cube project. Thanks.